You discussed with me and with Meta. I'd like to remind you that the idea is that we have inputs in some n-dimensional space, and we know that if the number of examples is sufficiently large, we probably will not be able to find a hyperplane that separates them in an n-dimensional space. So we embed the inputs in a larger dimensional space by converting them, by applying some transformation into m numbers, which are, each of them is a function of the input. So this will be x1 to xn. This will be a function phi1 of the whole vector x. This will be a function phi m, the whole vector x. So each function depends on the inputs. This does not work. Okay, and then typically the dimensionality m will be larger than n, maybe much larger. And then we know that, if the number of examples is smaller than m, then we're guaranteed to find a separating hyperplane in this space. And that's what we do. Okay? And so now we use the phi's to actually find a perceptron. Now, these functions have to be nonlinear. Why? Because if they are linear, we're actually still implementing a linear transformation from the n inputs to this output unit. And the reason things fail when the transformation is linear is that we really want to guarantee that we will have a hyperplane here. We want the points here to be in a general position. So, if this is a linear transformation, and we say have a number of examples here which is larger than n, then in this space the points will not be in a general. They will be maybe in a general position, but we're not in a situation p is larger than n, so we're not in a situation where the perceptron where there is a solution to the perceptron problem, where there's a separating hyperplane. Now, if the transformation from here to here is linear, then in this space the points are not going to be in a general position. Okay, and then this is why things fail. But if we have a nonlinear transformation, typically, if we choose our nonlinear transformation, if it's really nonlinear, then typically the points will be in a general position here, and now if the number of examples is smaller than the dimensionality, we're guaranteed to have a separating hyperplane. Okay, so this is the idea. And one other point that I probably made it last time, but I'd like to repeat it, even if I did, is that this whole thing doesn't make any sense if the function that the dichotomy that we're trying to approximate has no spatial structure. If the points, if the points were categorized randomly, then the fact that we're guaranteed to find a hyperplane just tells us that we're not going to be able to generalize at all. The whole thing makes sense because we assume that the function that we're trying to approximate is smooth in space. And therefore, if we're categorizing all the points correctly, we're likely to categorize points in the vicinity. And so what we're really doing is we're taking a problem in n-dimensional space for which it's hard to approximate the separating surface by plane. And by transforming it in larger dimensional space, it's much easier to approximate the separating surface as a plane. Okay? And we're using the support vector machine for the same reasons we used it when we initially introduced it. We assume that the function is smooth in space, so we want to find a hyperplane which is further, as far as possible, from all the points, so that it will be likely that the generalization will be good. Okay, so this is what we're doing, and then the next thing that we discussed, so we have this transformation from Rn to Rm, and the next thing that we discussed is that, in fact, if we're solving the problem, what we call the dual problem, then we're really solving a p-dimensional problem. So the fact that we increase the dimensionality by a lot is not making life much more difficult for us. Everything that we did with a support vector machine carries through to this problem with just one slight change, and that is that when we apply the function approximated by the network, and when we implement the Adatron algorithm, whenever we encountered quantities like that we called x mu nu, which were x transpose, let's look at it differently. X mu. Whenever we encountered something like x mu transpose dot x nu, we replace this by k mu nu, or by k of x mu x nu, which is phi transpose of x mu phi of x nu. So this is a scalar product in the m-dimensional space, and everything is still easy if we know how to calculate this kernel. One way to calculate this kernel would be to explicitly calculate each one of the phi and do the scalar product. But there are many cases where we actually don't need to do it. We can do a simpler calculation in the n-dimensional space in order to calculate this quantity. So the example that I ended with last time was the following kernel, k of x and y was 1 plus x transpose y to the power of 2. To calculate it, we do a scalar product of two vectors in n-dimensional space. But this really corresponds, we showed that this corresponds to a scalar product, or an inner product of two vectors in m-dimensional space, where the vectors, so this corresponds to phi of x, vectors phi of x, which are 1 square root of 2 x1, square root of 2 x2, up to square root of 2 xn. And then, let's see that I'm getting correctly the prefactors. X1 square up to xn square. And then we had all the mixed quadratic forms, square root of 2 x1 x2, up to square root of 2 x1 xn, and we also have square root of 2 xn minus 1 xn, all the combinations, and I think that's it. So the dimensionality of these vectors, what is it? It's 1. So m here will be 1 plus n times n plus 1 over 2. it's very, now another way to think about this kernel and this transformation is that what are the linear combinations of all these functions? What kind of functions can I generate? So even if we, we train our support vector machine with a kernel method using this kernel, we're implicitly training a linear support vector machine on this space. And so the function that this neuron is calculating is some linear combination of these functions, and then it's doing the thresholding to decide whether it's +1 or -1. What are the linear combinations of these functions? Yeah, it's all the second-order polynomials over what? Over the entries of the vector x, right? So it's second-order polynomials over an n-dimensional vector. That means that this kernel, this architecture with this kernel can precisely implement any separating surface which can be described as a second-order polynomial. Okay, it's actually quite okay. I have another comment, but I'll keep it for a few minutes from now. So now it's also possible to generalize this kernel very obviously by taking x transpose y to the power p. This whole family of kernels is called polynomial kernels.
Can you repeat the second-order polynomial comment?
Yes. So what will this unit calculate? Who asked the question? Aviv?
Yes.
Okay. What is this unit calculating? It's calculating a linear combinations of these quantities. Each one of them is one of these functions, right? Any polynomial over the second-order polynomial, quadratic form, over the variables x1 up to xn, can be written as a linear combination of these functions. These functions span all the possible polynomials. And then this unit is thresholding to decide whether it's +1 or -1. So this means that, again, the separating surface, which is the positions at which this function, this linear combination, is equal to 0, can be any second-order polynomial. Meaning that this architecture can implement any function for which the separating surface is a second-order polynomial. Okay, now if we generalize to p dimensions, to a power p here, then I will not do things explicitly, but you can convince yourself that we can implement any p-dimensional polynomial. Can implement precisely any p-dimensional polynomial. This is why these kernels are called polynomial kernels, and this gives you also some intuition why having a higher dimension. We'll talk about m in a moment, but m becomes larger as we increase p, allows us to approximate more complicated functions. Now, what is the dimensionality m of the embedding space? Well, I will leave this as maybe as an extra bonus exercise for you. I will write down the answer, okay? But you can think about it. The answer ends up being n plus p over p, if I'm not mistaken. Let me check my notes. Yes, n plus p over p. You can see that, you can check that this is for p equals 2, you will get this answer. And you can think about it, why this is true. This is really a question in combinatorics. Yes?
Yeah, but how do we know that there is such a function which will give this exact term?
Oh, okay. So this really, your question really leads me to the next topic. But before I answer it generally, here, the way we saw it, that's a very good question. Here, the way we saw it is that I started from this. So I had the explicit set of functions, and I showed that the dot product in this space corresponds to this function. You can also do it for this. Okay, I'm not doing it, but you can do it and find what are the functions. Okay? But now this really leads to another question. Can I just decide on some k of x and y as I wish, and will it correspond to some dot product in some higher dimensional space? So there are some properties that k has to fulfill in order to be a dot product. So obviously not every k could work. For example, a dot product has to be symmetric with respect to a replacement of x and y. But if it's symmetric, can any k can be interpreted as a dot product in some higher dimensional space? So that's a good question. So if I give you some k, is there a set of functions in some higher dimensional space with a dimensionality that we don't necessarily know, but is there some dimensionality and a set of functions such that this is equal to phi transpose of x, phi of y? So this brings me to a theorem that actually states under what conditions this is true. Okay, so suppose that we have a vector x, and we assume that x is confined. Okay, so x is confined, meaning that the entries of x cannot go up to infinity. They're limited to some finite range. We'll assume for simplicity that it's confined to an n-dimensional box. The vectors x are confined to an n-dimensional box. And we're given some k of x, y, some function of two vectors in this that both are in this box. So the theorem states that a series of functions phi 1 of x, phi 2 of x, and so on, exists such that k of x, y is equal to sum over I, phi I of x transpose phi I of y. If and only if so one condition is something that I mentioned, that k has to be symmetric. Okay, you noticed that I didn't write an upper index, and I didn't write it because it's not necessarily finite. I will come back to that. And the kernel has to be symmetric. Okay, symmetric. And the other condition is the following condition, which we will in a moment discuss in more detail, that the integral of k of x, y, g of x, g of y, dx dy is at least as large as 0, it's non-negative, and finite, it doesn't diverge, for all choices of the function g. Okay, now, what does this, so one thing that you have noticed again is that I did not write here I going from 1 to m, and this is because it could be that the kernel actually has infinite dimensions, that you have a series, an infinite series of functions. The kernels that we discussed here, for these m will be finite, but it's easy to write valid kernels which can be, we'll mention some possibilities later, which can be written in, as in terms of a series of functions which is infinite. Now, can anyone tell me what is actually written here? Does this remind you of something, some definition that you know? G, okay, so G is any function.
No, like the large G that we have, it's really similar to that we used when we do problems.
Okay. I'm not. Maybe it's similar, but I'm not necessarily saying it. What does this tell us about K? What are we doing here? We're taking some function G, and we're doing something like a quadratic form with G. We're taking any point, any point in space X. We're looking at G at that X. Any other point Y, G at that Y. We're multiplying it. In this sense, it's a quadratic form, and with some coefficient that depends on X and Y. And then we're summing up over all positions X and Y. Does this remind you of something? Anyone? Okay, so I will try to lead you to the intuition. And if I would tell you that a matrix has the property. Oh, thank you. Who said this? Gal? Okay. So this is all I needed to say, matrix. If I tell you that for a matrix, you can choose any vectors, let's still call it G, but
G doesn't have to be linear.
Wait. Okay, so if I take some I take any vector, so analogy for finite vectors. So, suppose that I have Gi, I going from 1 to n, and I tell you, and I have a matrix K ij, which is n by n, and I tell you that sum over I and j, K ij, Gi Gj, is at least as large as 0 for any choice of the vector G. This is what we call K is positive. The definition of a positive semi-positive, yes, thank you, semi-positive operator or matrix. Okay, so now you can think of a function of x as a vector in an infinite dimensional space. Instead of the discrete index xi that you have here, so we have here, G, we have here n numbers labeled by the index I. If I give you a function G of x, this is actually an infinite number of numbers labeled by the index x. For each choice of x, there is some G. Okay, right? So you can think about G of x as, instead of a vector labeled by a discrete index I, think about it as a vector labeled by continuous index x. Once you acknowledge that, you can see that what is written here is actually very similar to what is written here. We're taking all the choices of the index x, all the choices of the index y. We're taking the value of g at this, for the index x. We're taking the value of g for the index y. We're multiplying them and multiplying by some number which depends on x and y. This is like the kij. So the fact that g is nonlinear doesn't matter at all, right?
But you do assume that it's like in a Hilbert space.
Okay, so now, this is not a course, very far from a course in math, and I'm not being precise, but I just want to give you the intuition. So this definition is really a generalization of that definition, and now, here we're not going to call K a matrix. It's not a matrix. It's indexed by two continuous variables, but we're going to call it an operator. So this is a semi-positive definite operator. So again, Mercer's theorem tells us that if K is symmetric and is a semi-positive definite, meaning that it obeys this quantity, there is some space, there is some set of functions, maybe infinite, that can be in principle found such that this K of xy can be described as a dot product in this over the vectors phi.
Requiring that x be confined troubling us?
It could be, if we, but in most practical problems, our input vectors, we can assume that they're confined to some range.
So this means we won't be able to generalize,
Yeah, right. So if the x and y can be in an infinite dimensional space, it could be that there is no series of functions in this sense that can be found.
I mean, x and y are in an n-dimensional space, what you're saying. Like, is there...
The x, that has nothing to do with n. This has to do with the values of the entries of x. So the entries of x, each one of them, we assume that they're confined. Okay, that's our assumption.
Does the theorem also give, I think, this algorithm defined?
Yes, and I will mention it in a moment, but I'm not sure that it will be easy for everyone to follow it. So you probably studied quantum mechanics. Who else studied quantum mechanics here? Okay, so for those of you who studied quantum mechanics, the whole relationship between this and this should be more clear than for those who did not. And in fact, the functions phi, I will just mention it, and the functions phi are nothing but the eigenfunctions of this operator. Okay?
What?
Eigenfunctions of this operator. So, the functions phi, and this is, I'm saying this mostly to those of you who studied quantum mechanics, because for you it will be, the same tools are used extensively in quantum mechanics. Phi are eigenfunctions of the operator K, meaning that each one of them has the property that the integral dy, let's do x, the x, k of x, y, phi of x is equal to some lambda I, okay, so let's put an index here, lambda I times phi of y. Remember what I did in this analogy. You can see that what I'm doing here is similar to multiplying the matrix K by the vector, G. And this equation tells us that the vector, each one of the phi i's, I should put here an I, is a vector such that when we do this kind of multiplication of the matrix by the vector, we get the vector times a number. So this is like an eigenvector equation. Okay? So in fact, again, the phi i's are nothing but the eigenfunctions of this operator. Now you are actually Gal, you didn't study quantum mechanics. Okay, but some of you might see why the assumption of confinement might be important. Think of, for example, about the.
Is there like an algorithm to find these? Like I know the algorithm.
Okay, so finding this is not necessarily so easy. It's solving an equation which is not necessarily easy. But just think, think about some examples that we. So again, and now I'm talking mainly to those who studied quantum mechanics. Think about finding the eigenfunctions of the Laplace operator. If we're in a finite dimensional space, we have a discrete set of eigenfunctions. These are the Fourier. It's a Fourier series, so there's indeed a discrete set. It's infinite, but it's discrete. But if we're in an infinite dimensional space, it's not discrete. Right? So this kind of gives you an intuition why the confinement was important.
So to follow the problem, if we're looking at input neurons, sure, X is
A lam, right? Yes. Yeah. Okay. Yeah. But I'm just more formally, I wanted to relate this to something that you know.
This also means that there is only one way to break K into a dot function, right?
It definitely seems to suggest this, and I think that this is, well, if some of the eigenvalues are degenerate, then you have a choice to, I think that you have a choice. So, okay, but this was really just, I'm sure that for some of you it would be difficult to follow what I said here, but the most important thing out of what I told you is just the knowledge that there is this very simple criterion, and you can cook up any kernel that you want if you can show that showing that it's symmetric is of course easy, but if you can show that it also obeys this criterion, then you might not know, you might not be able to solve this problem and find what are the functions, but somewhere there are these functions exist. If you implement this kernel, the k of xy, you're actually implementing a dot product in some higher dimensional space, which might be infinite. Okay, so now I really want to just make some summarizing comments and finish discussing the kernel method. One thing, I'll just give some examples of some commonly used nonlinear kernels. One is called the Gaussian kernel. So it's a Gaussian function of the difference between the distance between the two vectors x and x prime. It's sometimes called also radial basis function.
Sigma is just whatever we choose for.
Yeah. So in general, there's a question, how do you choose either the functions phi1 to phi m, or how do you choose a kernel? I'm not going to discuss it. I mean, and often, they're not very good formal criteria, but there are some heuristics. People know that for some types of problems, some types of kernels work well. This term, radial basis function, is sometimes used not for this specific function, but for any function which depends on the distance between, the vectors x and x prime.
Is it square?
Yes, it's squared. Yes, thank you. For any, so sometimes this term used for any function of x minus x prime. Maybe I would put here also two lines to remind you that it's it's two vectors. Another set of kernels which is very often used are the polynomial kernels. We discussed them. 1 plus x prime transpose x to the power p, or to the power d. And then logistic function, that's also sometimes used. Now, the logistic function, one of the reasons that the logistic function is interesting is that it kind of corresponds to what neurons can do in simple models of neurons. Maybe I will elaborate on this in a few moments. Now, the logistic function, so just a few things. The radial, if we ask what is the dimension of the embedding space, here it's infinite. Here it's finite. I wrote down what it is at the beginning of the lecture. Here, this is not guaranteed to be a valid kernel if you choose, beta and b as you wish. But it is for some choices. So it is a valid kernel it's a positive definite kernel for certain choices of beta and b. Yes?
Can you elaborate at least, briefly about the intuition of where to choose any kind of kernel?
I wish I could, but I myself don't have a very good intuition. It's not, I don't work in machine learning, and I don't have much experience myself using the support vector machine. But I think that really in reality, people just choose something. It's not. I know that the radial are considered very good, but I think that even if you ask someone who's an expert on this, he'll have a hard time explaining to you which kernels work well when. But there is a nice intuition about the polynomial that I mentioned, that it really precisely approximates any polynomial surface. Not approximates, it precisely implements any polynomial surface. Okay, what else did I want to tell you? Okay, one thing that is quite important is we can decide on a kernel, or we can decide on the set of functions that, the functions phi1 up to phi m, and then it's clear what are the rules of the game. There are these functions, and we're trying to find a separating surface in this a separating hyperplane in this space. And then you can ask questions, about how, if you have some assumptions about the function that you're approximating and about the distribution of the inputs and so on, you can ask questions about how well this architecture will implement, and about the function, yeah? How well this architecture will be able to implement the function, to generalize, and so on. I would like to emphasize that if we are free to choose the functions phi as we wish for any given set of for any given set of examples and any problem, then the question is meaningless. Why? If there is no constraint on the functions phi, I claim that any questions about the capacity, the ability of this architecture to implement a dichotomy is completely meaningless. Can someone tell me why I'm saying this? Why am I being so negative?
When you don't have any constraints on the number of dimensions.
Yeah, no constraint on the number of dimensions, no constraint on the phi. I claim that any dichotomy can be trivially implemented under these conditions.
Well, yeah, you define the separating surface, just the circle by something really nonlinear.
No, but in this, the separating surface has to be a linear surface in the space of the phi.
Yeah, but if you have no constraint on phi, then you could.
So how can you see this? I claim that you can see this even more easily. Yes, Daniel.
You could attribute a separate dimension to each point.
Okay, even easier. So I give you some dichotomy, and I want to construct a very, very simple implementation of it using this architecture, and I'm allowed to use the phis as I wish. What can I? Yeah, just choose. I claim that you need just one unit here. You don't need any number, just one, and choose this function to be a function which is positive, for all the points which should be categorized as 1, is negative for all the other ones. So, trivially simple architecture, just one function, can implement any dichotomy by definition, right? So that's why I'm saying if there are no constraints on the phi, it's obvious that any dichotomy can be implemented, and there's no interesting question to ask about how well this architecture can implement. It can implement anything. So the interesting questions really arise only when we have some constraint. We assume that we calculate, we use some particular set of functions, we use some particular kernel. Then you can ask, if you define also the statistics of the inputs, define also the properties of the functions that you're trying to approximate, how well you will generalize and so on.
So we have an idea how the training set is representing the real data set.
Yeah, exactly. So, we discussed these kinds of questions a bit earlier when we discussed the linear approximation. You have some training set. You can ask, how well are you going to, you're implementing this, you're training this network. How well are you going to generalize? These questions become meaningful. My point is, these questions can be addressed. They become meaningful if you have clear constraints on the phi, and you also need to decide to have some assumptions on the functions and on the input space. Okay, but we're not going in any depth into these questions in this course. Yes, Al.
Is there like a way to give penalty to adding more degrees of freedom to the functions or increasing the dimension, so we'll get some sort of optimal?
That's a good question. Possibly, I don't know, but it seems like something that would make sense to do it. So, but I don't know if people are actually doing it. Very often when people implement a kernel method, they're really just starting from a kernel. So the kernel explicitly, really implies a certain set of signs. I just want to finish with one point, and that is that if we put learning aside for a moment and just ask, what do we need to do when we want to apply this? Suppose that we trained our network, we trained our coefficients, our coefficients here. Phis are fixed, but we trained our coefficients here. And we have here one description of how to calculate the output, right? One description which is written here is that we calculate the phi based on each one of the x's, and then we sum these linearly with some weights, and then we threshold. So here we're passing through an m-dimensional space, and but remember that we had this description in the dual problem. So I would like to point out that once we know the coefficients, in the dual problem we can also kind of represent the calculation which is being done in a similar structure. We have our inputs x1 up to xn. And now what do we need to calculate? In order to calculate, remember that we had y being equal to the sine of sum over mu, alpha mu, y mu, k of x mu. Right? These are the examples. So we trained based on a set of examples. Now we're done with that, and we want to calculate, what is our approximated dichotomy doing for some general mu x. So this is what we need to calculate. So we can represent it as follows. We need to calculate p quantities. What are they? They are, this one, for example, would be for a given x is this vector. For a given x, it's k of x, x1. The last one would be k of x, xp. So this is a number of examples. Okay, so these are p points. And then we need to sum these quantities with linear coefficients. Let me call them C1, C2 up to Cp, and threshold. What are the linear coefficients? C mu is equal, we read it from here, C mu is equal to alpha mu y mu. So in some conditions, you can imagine that perhaps this kind of calculation is done by a neural network. So remember the logistic kernel that I described at the end. Unfortunately, it was behind what is written here now. I erased it, but if you can look at your notes, if we use a logistic kernel, then what is actually calculated by each one of these points is some linear combination of the x's multiplied by something, adding some number, and then passing it through a sigmoidal function. And this is kind of what we often model as what neurons are doing. So therefore, this just gives you some perspective that the calculation which is being done at the end in a p-dimensional space could be interpreted as, a calculation which is being done by a linear network with, the input layer, an intermediate layer, and output neuron, and the intermediate layer has now p neurons in it. It's an interpretation, possible interpretation in some situations. Okay, so let's take a break now, 15-minute break, and continue with a new topic afterwards.
הסתמכנו על כלל ההחלטה לגבי אלפא ניו, נכון? ואז באמת אמרנו שאם הדבר הזה קטן מאפס, אז הוא בטוח...
אתה מדבר עכשיו על המקרה השני, נכון?
המקרה השני. בסוף אמרנו שדלתא אלפא ניו חייב להיות גדול שווה לאתא כפול 1 מינוס דלתא ניו. ואז לא ברור לי הצד שעשינו עכשיו.
אז אמרנו, כמו שאמרת, הדלתא אלפא ניו היה גדול שווה לאתא כפול 1 מינוס דלתא ניו. למה גדול שווה? כי הוא המקסימום שווה במינוס אלפא ניו. אז עכשיו, מה שאני עשיתי זה שאני החלפתי, פה אני השארתי את הדלתא אלפא ניו כפי שהוא, ופה אני החלפתי את 1 פחות דלתא ניו, אני פשוט כתבתי את זה כך, 1 פחות דלתא ניו קטן שווה לדלתא אלפא ניו חלקי אתא. ועכשיו, אבל זה מוכפל בגודל שלילי, דלתא אלפא ניו במקרה הזה הוא שלילי. ולכן זה הופך לשים עליו, ולכן אני יכול לכתוב שדלתא קיו גדול שווה לדלתא אלפא ניו כפול.
זה מה כן.
וההיפוך סימן הזה, זה מה שהסתכלתי עליו בשיעור שלפני זה.
זה הדבר שהוא כאילו לא אינטואיטיבי, ואתה ברגע שאתה קולט אותו בכל טריוויאלי. אוקיי, תודה רבה.
אני רוצה לראות pictures, תמונות. אני רוצה כן, לראות תמונות. Hello? Are you sitting here? Hello? אתה מבין גרמנית, אנגלית, רוסית? אוקיי, אני רוצה לראות תמונות כיסא קלה בתקופה. יש תמונות? אוקיי. אין תמונות באינטרנט?
יש לי עכשיו, בלי דוגמאות, כולם נמצאים.
אוקיי, תודה רבה.
זה פים שלך, נכון?
כן. זה פי X, אבל זה לא פי I. כאילו פי I זה...
לא, נגיד זה פי I.
אוקיי. אז תבין, אז אני מקבל פה, הוא לא תלוי בכל ה-X, הוא תלוי רק
בכל הדוגמאות. באיבר הראשון של כל הדוגמאות.
כן, הבנתי.
אז שואל למה?
לא, עכשיו הבנתי מה אתם עושים. X1 זה האיבר הראשון בכל הדוגמאות.
כן, אבל כל פעם אתה מכניס לפה דוגמה אחת, אז אתה מקבל את הפי עבור אותה דוגמה.
כן.
את המיפוי של אותה דוגמה למרחב העניין-נדי.
הבנתי. כן, הקרן הזה ממש רעיון גאוני.
נכון. לא, שאולי כתוב שם משהו אחר, שגם לכתוב את השם שלנו.
so the next topic I would like to discuss is gradient-based learning. And the first thing is I'm going to switch now to, I'm going to present this in the context of approximations of continuous functions. As in the, the linear perceptron, the first topic that we discussed. So imagine that we have a continuous function x going to some scalar function of x, and this is what we want to approximate by some linear network.
Is this like a
Well,
boring topic?
well, it's still supervised learning, but it's we're finished with the kernel level and with support vector machine.
And we're still talking about perceptron or not?
It's a bit more general now. Okay, we will see. I will want to focus on briefly on some particular network architecture, and you will see in a bit later. But we're discussing again a continuous function. We have some neural network that we want to train to approximate this function. So, but what this neural network can do, it can take x and it can transform it into an output y, which is some function of x and the internal weights within the network. So we're going to imagine that we have some prescribed architecture for the network. Each unit in the network does something, but each unit in the network, the output of each neuron in the network depends on its inputs through some weights. So these are the variables that we're going to vary as we try to make this network approximate well this function. And so our goal is to learn the W base that will allow our network to approximate this function based on examples. And so our examples I will denote by x mu and y mu. In my notes I have, because of the way I did it in the last year, I have here y0 nu. So if I write, when I continue to write, if I write a 0, please alert me and don't be confused. Try not to be confused by it, but the best is to alert me. I want to use the notation where I just call it y mu. And y mu is really, f of x mu. So these are the examples. And the approach that we're going to take, I think here I can still write. The approach that we're going to take is we're going to try to minimize the training error. So all this should be familiar to you. The training error is a function, we regard it as a function of the W's, and it's defined as 1 over p sum from I going to, or mu going from 1 to p. And what the network is generating for the vector x mu minus y mu squared. Okay, so all this is familiar to, you. Why am I doing it again? Because we discussed it in the context of the network, which is one outputting unit, which sums up its inputs linearly. So the linear function of the inputs. And for that problem, it turned out that minimizing this training error just led us to a set of linear equations, right? We were able to solve this set of linear equations and that's how we found the optimal W. But if the calculation which is done by the network is more complicated and involves nonlinearities, then typically we do not know how to, to explicitly find the minimum, analytically find the minimum of this training error. So what can we do? So one very common approach is to try to minimize it, in a sense numerically, by trying to gradually approach, to move in the space of W's in a direction that will minimize the training error. And I'm going to discuss, so this is really in some sense this is a very general problem that occurs in many contexts, both in machine learning and in various other contexts in science. We want to minimize some multidimensional function. We know how to calculate it, but it's complicated. We don't have an analytical expression for the minimum. An optimization problem. And the approach that I want to discuss is perhaps the most simple one. It's what is called gradient descent. So the idea in gradient descent is to go in steps, and in each step we change W by going in the direction of the gradient. The gradient of what? The gradient of the training error with respect to the elements of W. So I remind you that in general the gradient is the direction in which this function changes the most rapidly. And so we're going down in that direction and hoping to reach eventually the minimum. Okay? And there is a problem in what I said. I said the minimum. But in many cases, one of the difficulties in applying this approach is that there are multiple minima. So we're not guaranteed, when what we do is gradient descent, we're not guaranteed to reach, we are guaranteed to reach a local minima of the function, but we're not guaranteed that this is the global minimum. But, okay, that we're keeping that in mind, it's still something that we can do. So I didn't write it. So delta W is just minus eta. Eta, we used it in the past to denote the learning rate. Minus eta times the gradient with respect to W of the training error. And we basically continue to iteratively do these steps until we find a W for which the gradient, we reach a W for which the gradient of the training error, until W is W star, for which this is 0. And in reality, this is just a moment. In reality, this is not what happens. I mean, we approach a point where we come closer and closer to the point where the gradient is 0, and perhaps we stop when it's sufficiently, the changes in W become sufficiently small. Yes?
Why we don't just derive the training error equated to 0, look at all the minima and outlaws fewer options, which is worst case we can even numerically approach.
Okay, sounds like a good plan. Why don't we just take this training error and kind of scan it over all possible values of W and find where it's minimum?
Harder computational.
Okay, so typically W is a multidimensional quantity. So imagine, say, that you have 10 W's. And W's, first, you know that they range between 0 and 1. So you can discretize, the range between 0 and 1. And suppose that you discretize very coarsely. 10, you want to check how this function looks like for W, for the weight equals 0, 0.1, 0.2, 0.3, up to 1. So you have 10 values. Maybe 11 is the way to describe it. But you have 10 of them. So how many combinations of W do you need to check? It's 10 to the power 10. So the problem is that the big problem in any optimization problem in general is that once that you're optimizing in a high-dimensional space, and high doesn't have to be 100. High is already, when you're trying to scan a space which is 4-dimensional, 5-dimensional. The number of combinations that you would need to scan in order to really go through all the possibilities is huge, and it's not practical. It's not something that you can do. Okay? And that's why optimization in multi-dimensional spaces is hard. Okay, so so this is gradient descent, and this is something that can be done. And now I want to mention a particular architecture which is very commonly used in machine learning. And this is the following architecture.
Is the eta constant in time, or?
Okay, so this is, there are different variations of, I'm really just writing down the most simple-minded approach. You could imagine using a fixed eta, but often it's beneficial to adapt eta as you approach the point. I will discuss this a little bit in a next lesson when I will discuss stochastic gradient descent. I will actually address this. If you're just interested in multidimensional optimization, it's worthwhile to know that there are significantly better algorithms than simple gradient descent. For one thing, it turns out that if you always go into the direction of the gradient, it's often quite inefficient. It sounds like the best thing to do, to go in the direction where things go down as fast as possible, but in fact it's not the best thing to do, and there's a modification of this idea called conjugate gradients, which end up converging faster. And then there are, and if you want to avoid local minima, there's a whole set of different approaches to optimization that try to really kind of first coarsely span the space to avoid, to be able to jump from one local minima to another deeper local minima, and then at the end converge to the minimum. So it's a whole.
Is there a deterministic algorithm that converges faster than the gradient?
Yeah, conjugate gradient converges faster. It's possible to prove that it converges faster than.
And it's deterministic.
Yes. So it's fairly easy to analyze how these algorithms behave when you're already close to the minimum, because then you can approximate the function basically as a paraboloid, and then you can ask how fast. Then it's possible to analyze precisely how many steps will you need to converge. If any one of you just encounters optimization problems or other numerical problems in general, this is outside the context of learning. Optimization is a very, very common issue that one encounters. There's a book that I like a lot, which is called Numerical Recipes. It originally came out, I think, as Numerical Recipes in Fortran, but then it came out in various editions in C, C++, Pascal, and various. The latest edition that came out is probably in C++. Well, so it's in the language of your choice. But the book contains actually code that implements many numerical algorithms, but that's not the reason that I like it. The reason that I like it is because each topic which is covered in this book has an introductory text, which I like a lot. It's not too formal. It's not like proof theorem, but it's sufficiently rigorous that you understand really the principles behind the algorithms. So it's a very good way to quickly learn about the principles of various numerical algorithms. Okay, but this is really a side comment. Okay, now what I want to do now is discuss a particular architecture which is very commonly used in machine learning, and this is what is called feed-forward networks. And then we'll discuss gradient learning for feed-forward networks. So the idea is that you have your input units, x1 up to xn. And then we have multiple layers of units input units. So, and then we have another layer of units which does the same to the output of the second layer, and then we might have another layer and so on. Okay, so let's just denote by sigma 1 the outputs of these units. Sorry, this is a bit messy, so I write it here. Sigma 1 the outputs of these units is a vector. Sigma 2 is a vector of the outputs of these these units. And sigma L will be the vector of outputs of these units. And in general, we might consider this as the output of the network.
Is the number of neurons in each level constant?
Not necessarily. Okay, so we call these layers the hidden layers. So there's the output layer, which is this one. So I would also call the outputs of the network maybe y vector.
And they're also not necessarily n.
Not necessarily n. In fact, very often it will be 1. So if we want to discuss this in the context of what we did here, where we want to approximate the scalar function, it will be one unit, one output unit. So this is the output layer. This is the input layer. And all the layers in the middle are called the hidden layers. Why? Because if you consider all this as a black box, something that gets inputs and produces outputs, you don't see the activity, what the values of the outputs of the units in the hidden layer, the hidden layers. And so this is, we would call this a network with L layers. And what I didn't yet tell you is what each one of the units is doing. So typically, we assume that the neurons themselves, or the units, are sigmoidal. I'll call them either units or neurons. So that means that sigma IL is a function of...
Everybody must be connected to all the neurons in the
Principally, yes. So each neuron in each... This is the architecture. Each neuron in each layer receives inputs from all the neurons in the previous layer. And the output of this neuron is some nonlinear function of the inputs from the previous layer, but they are weighted with linear weights, Wi, J, L, sigma J, L minus 1, sum over J. Now I'm not writing what are the limits of the index J, because it depends on the layer. I don't want to introduce too much notation, so I don't want to give a name for the number of neurons in each layer. So this will go J, the number of values of J is the number of units in the previous layer. So this is a sum over J, and there might be some bias, BIL, which depends on the neuron. And the function G, typically, I wrote that it's sigmoidal, so when I say that the function is sigmoidal, it means that it's a function which goes to 0 for large negative values, it goes to 1 to large positive values. This is 1, smoothly and monotonically goes from 0 to 1. And very often, people work with a hyperbolic tangent.
Which is from minus.
I guess I would have to take a hyperbolic tangent. Let me write for proportion of the tangents hyperbolic of x. Okay. Now, if we think about the optimization problem that I described here, then the parameters W should be mapped actually here to two sets of parameters. It's both the weight that you see here and these biases. Okay, we're free to vary both. If you want to really reframe things such that you only have weight, you can think about it as if each neuron also receives an input from an additional neuron whose output is always 1. And then you can think about this as a weight with respect to that neuron. And then you can think about all these parameters as weights. But it's meaningless. It's just a weight to write it. Okay, so now why introduce these types of networks? So for one thing, it's possible to show that these networks can do much more than a single linear perceptron. And in fact, it's not necessary to have many layers. It can be shown that a network with just one hidden layer can approximate any function. So this is important to know. If you want to ask yourself, do we limit ourselves in some sense in terms of just what can be represented at all? Which kind of functions can be represented at all by this architecture? Do we limit ourselves? In some sense, the answer is no. There is a theorem which came out actually only in the 90s. Referred to as universal function approximation theorem. And I will put it on the Moodle, Baron, 1993, and which in simple words says that a network with one hidden layer can approximate any function at any desired accuracy. But of course, there's a lot of fine print below this statement, and I'm not going to write it down explicitly. I'm not going to describe exactly what are the conditions, but I will kind of tell you what they are, and I will just try to write it down a bit more formally. Alex? No? Oh, okay. So actually, a network with one hidden layer means that the output of the network can be written as a sum over L going from 1 to M, M being the number of units in the hidden layer, A, L, hyperbolic tangent of sum over W, these are the outputs of the neurons in the hidden layer. Then we're summing them with some linear weights, maybe adding some constants. So this is what a network with one hidden layer can do, and with neurons with this particular type of nonlinearity. So the statement says that these are the rules of the game. This is the architecture. This is the kind of functions that we can implement. The parameters are the W's and the BL and the number of units, M. And the theorem involves some assumptions on the function. I will not write them explicitly, but smoothness, bounded. This is very important. Function has to be bounded, and it's also defined in some finite space. Defined in a finite box. Okay, but under the appropriate conditions, which again are specified more clearly in the theorem, there exists a set of parameters, which are the W and J, the BL, the AL, and the C0. Such that the mean square error averaged over the input space it can be made as small as possible as a function of n. So what this, in words, what this tells us, which sounds actually great, it tells us that if we increase the number of units in the hidden layer, then we can make the error as small as we wish. And this parameter, this A is of course a property of the particular problem that we're trying to solve. But there is a caveat. So, yes?
Looks not so different than logistic kernel.
Yeah, it's very similar. This is why I brought up the logistic kernel in the first place. So the theorem tells you again that with one hidden layer, I give you some function. You can, if you have enough neurons in the hidden layer, you'll be able to approximate this function to any desired accuracy. Sounds great. The problem is that the question is how large should M be? And this is set really by this coefficient A. So the not so nice thing about this theorem, I'm sorry that I'm continuing here, is that A, what?
A some constant?
Yes, A is some constant that depends on the problem. But without being too precise, I will tell you that A, the dependence of A on the dimensionality of the problem is very, very sensitive. So A goes increases exponentially with the dimensionality of the problem. I can give you my intuition why that is the case. Why, essentially the number of neurons that you need in the hidden layer increases exponentially as the number of units in the input layer, as follows. Imagine that instead of sigmoidal functions, the functions that we had would be functions of this form, some bump functions. So this means that each unit in the hidden layer would be, it would generate an output only if its input lies within some narrow range. But we would be free to choose the position of this bump and its width. So then there would be a very obvious way to solve the problem. We could say we want to discretize the input space. How do we discretize the input space? We generate one hidden layer unit for each possible combination of the inputs. Okay? So, and maybe you know what, actually, maybe with one hidden layer it would be, I need to think about it a bit more carefully, maybe with one input layer it would still be difficult, but we could certainly do it with two hidden layers. So we could generate output units in hidden layers that respond only if the values of the inputs are in a very particular range. And then all we need to do is and then we have, for each combination of inputs, we have one essentially unit in the layer before the output which generates a value. And then we just need to set the coefficient of that to the function. And I'm being very sloppy in what I'm saying, but I just want to give it an intuition. The problem is that then the number of units that we need we need to span all combinations of the inputs. And this goes back to exactly the same issue that I discussed when you asked me about optimization, that the number of possible combinations of inputs is exponential in the dimensionality. Okay? And so this is essentially, so this would be a simple way to generate an approximation of the function, but we need to really have a unit for each possible combination of inputs. And even though the implementation here does not explicitly do that, it just gives you a feeling for why the number of units in general, the number of units the hidden units that you need might scale in this way. By the way, the proof here is not a constructive proof. It does not tell you how to construct a network of sigmoidal units that will achieve this goal. I think that maybe after this paper came out, people also generated constructive methods to generate networks of sigmoidal units, maybe with more than one layer, a few layers. But I'm not going to talk about this here. There was some question, I think. No? Okay. But anyway, the main thing I want you to take out of this is the fact that in some sense, this is a completely universal architecture that can implement any function. However, the number of units that you might need to implement particular functions can be huge. And now, this also, you might ask, why did I put, so in principle, one layer is enough. If one layer can implement any function. But in practice, it turns out in reality that it's much better much easier to implement real functions that we want to learn with networks that have multiple layers. And this is related to two issues. One is perhaps having more layers reduces the number of units that we need to approximate a function. The other has to do with the learning algorithms. The type of learning that people apply to these networks is gradient descent typically. And the gradient descent might converge on some local minima. So the question of how well learning is doing, and then how well will the generalization look like, also depends on the architecture that we choose. And in fact, you might know that this architecture has become immensely popular recently in machine learning. It's now called deep learning, but it really has a very long history. So maybe I'll say a few words about that a bit later. It has a very long history. At this point, people have very weak understanding of what makes, why do particular architectures, in particular, why does it turn out, as has been learned in the past few years, why is it very beneficial to have very large number of layers. So people work, I don't know, networks with 100 layers. It works well, empirically. Why? There isn't no good understanding at this point.
But is there also a limit? I mean, at some point the network starts to
I don't know.
worse if you increase the number?
I don't know. Maybe. I don't know. I'm not an expert on machine learning. So I mean, in some sense, in this part of the course, I'm teaching you topics which are not what I do. But so I don't know. But I do know that there's very little understanding. But what I want to mention now is that if we go back to learning, and with that, I think if we go back to learning, what do we want to do? We want to minimize the training error over some set of examples in this particular architecture. So this means that for each example, epsilon mu is, it's half. Let's suppose that our output layer has 1 unit. No, okay, let's do that. Then epsilon mu is simply half y mu minus, let's call it the output, let's call it sigma. This would be sigma L, and there's just 1. So this is the training error of that example, and we want to, what we need to do is to calculate things like the gradient with respect to w I, j, here it will be capital L, the last layer, but we need, we need to optimize all the weights in the network. So we need to calculate things like d to the wij L, where L is any layer in the network, 1 over p, sum over p going from 1 to mu, epsilon mu. So this is 1 over p, sum over mu going from 1 to p, the derivative of epsilon mu with respect to wij L. Okay, so now the question boils down to, if we want to implement this, we have these equations, we know how each sigma depends on the previous sigma through the weight, and we want to calculate the derivative, and we care at the end only about the last sigma sitting here, so we imagine that there's just one of them, sigma L. We want to know how sigma L, what is the derivative of sigma L with respect to any one of the weights. So it's easy to calculate the derivative of sigma L with respect to these weights, right? Because it's explicitly written here. But then if we want to, but it also depends on the previous weights, because sigma L depends on sigma L minus 1, and sigma L minus 1 depends on all the weights on these weights, and so on. So actually sigma L depends on all the weights in the network. So it's a bit of a somewhat technical complication how to calculate this gradient. It's not really complicated. It's really application of the rule for derivatives of functions, right? It's a chain rule of derivatives, but you have to keep track properly of all the coefficients. So the algorithm that does that is called the back propagation algorithm. It's just a fancy name for a bookkeeping algorithm that calculates the derivative of this with respect to all these weights, and then it takes into account how these units depend on the previous weight, so it applies the chain rule, calculates the derivative of these units on these weights, and on these weights, and on these weights. You kind of go backward along this chain, and that's why it's called the back propagation algorithm, but it's just a name. It's a bookkeeping algorithm for calculating these derivatives. There's nothing very complicated in it, but it's a bit, technically it's a bit involved, and you will go through it with Neta. And so this really has become the basis of a lot of work in machine learning. I just want to mention a bit the history, because it has a kind of funny history, the back propagation algorithm and the use of these types of networks. So for as much as I was able to find, the history dates back to the 1960s, where the back propagation algorithm was initially discovered and described. It was not called back propagation, and people didn't pay much attention to it. It wasn't really noticed much. It was rediscovered in the 1970s, and then kind of rediscovered again in the 1980s. And in the 1980s, and I think the name backpropagation was used only at least from the maybe even after the 1980s. I'm not sure exactly when, but in the 1980s, people really started to apply these kinds of networks to interesting problems. Jeffrey Hinton and others started to use these kinds of networks to solve various problems, and it was successful, and it became very popular. Again, they trained these kinds of networks not with 100 layers, but maybe with a few layers to solve a specific problem. A little bit later, people came up with a variation of this idea, which is called convolutional networks for object recognition problems, which was also very popular. And then somehow, somewhere in the 90s, beginning of our century and the millennium, these types of networks became less popular. Other approaches in machine learning became more popular. And then in the recent years, suddenly there's a huge surge, and they're extremely popular again. And what has really changed in the past few years, with respect to what was going on in the 80s, is that the computational power of two things. Computational power of computers has increased immensely, so people can employ the backpropagation algorithm and some other variations of learning algorithms on very large networks. And people just tried using networks with 100 layers. Nobody could have done it in the 80s. The other thing is that the amount of training data which is available is also orders of magnitude larger than what was available in the 80s. So suddenly, these kinds of networks turn out to be very useful, can do very well in various machine learning problems. But essentially, nothing much has changed in the basic architecture, the feed-forward architecture and the use of the backpropagation algorithm. When we think about the brain, I think that the huge successes that are appearing now are very inspiring for us because something in this architecture is very reminiscent to what we think the brain is doing. On the other hand, we don't think that the brain is constructed from feed-forward layers of 100 layers. In the brain, we know that there are recurrent connections. We know that there are also, even in those cases where we know that information propagates as in vision from one brain area to another, we know that there are also strong connections going in the backward direction. But as I mentioned, even the performance of these feed-forward networks is not well understood from the theoretical point of view, and recurrent networks would be even more complicated. Recurrent networks, but when you want to discuss recurrent networks, things become recurrent means that information doesn't flow just in one direction. Then you have to be more careful also about how you even define the equations describing the network. But okay, this is just a comment. In any case, with Meta, we will discuss the backpropagation algorithm as I discussed, and then in the next lesson, I will discuss another variation of gradient descent called stochastic gradient descent. And I think that with this, we will end the supervised learning part of the course. Then in the following week, there will be no lessons and no lectures of me because of SSN, and then because of another conference. So we will only have a lesson with Meta on Thursday, the following week. Okay? All right. See you on Thursday.
Okay, ich wollte fragen, können Sie mir ein paar Bilder zu mir schicken von Kalasch, von Kissen